everyone. Today we have our another new episode and we will discuss on classical versus quantum, the evolutions of physics. We have our world famous speaker, Mr. Rob and Mr. David Smith. Mr. Rob, what you want to discuss about classical versus quantum computing?
Well, it's kind of an interesting discussion right now because the conventional knowledge up until just recently was that quantum computing was going to be a massive game changer and be able to do a lot of things that current computer technology couldn't do. And then we came up with generative AI, and suddenly we have the capability of doing a lot of those things with generative AI that we thought only quantum computers could do, because the generative AI gets to the solution in a far different way. It infers a solution as opposed to doing the heavy lifting in terms of mathematically calculating it. Now, the error rate in both processes can be problematic. With generative AI, we've certainly seen that those error rates increase over time. And at quantum computing, quantum computing errors have been the bane of that technology as well, though the class of errors are very different. But to put it in a very simple sense, what quantum computing can do is it takes where typical computing has ones and zeros. Quantum computing has ones, zeros, and a third state that can be either ones or zeros depending on how it's observed. The difference in education is rather dramatic. With classical computing, major in computer science will get you everywhere you want to go. With quantum computing, you need a solid foundation in physics. And I don't have that solid foundation in physics. So my strength in quantum computing is quite a bit less than it is in classical computing. The big advantage of quantum computing is it can take massive data sets. I mean, if you wanted to calculate weather with a high degree of accuracy across the world real time, it's believed that quantum computing would be the only way to do that using the massive data sets that you could collect on the different data elements. In other words, there's the idea that a butterfly flapping its wings in China may have an effect on the weather in California. Quantum computing can actually calculate that in theory if it can capture the data. Now, we go back to generative AI though, and with generative AI, it can do the same thing with models and inference. And then the question comes in, okay, which can do it faster and with more accuracy? With generative AI, it's using predictive models. With quantum computing, it's using just massive calculation power to do the same thing. Now, the bigger the data sets, the more quantum computing plays a role. It is really the strongest the bigger the data set. So if you wanted to calculate the mysteries of the universe, it's still likely that quantum computing is going to be the only way you're going to be able to do that. Other aspects of quantum computing that make it kind of interesting is the aspect of quantum pairs and teleportation. The idea that you can manipulate material of one part of the universe and have another paired material at another part of the universe with no respect to distance, and it would behave the same way. Current scientific experimentation shows that we've got some proof that this may work. We're a long way away from teleporting you someplace or another, and of course there's a whole hole we could crawl into with regard to whether teleportation will ever be viable, but at least for people. But this idea of a broad connectivity over great distances means that quantum computing could really have a major impact on real-time communications, because the data delay is non-existent. And so you're not talking about light speed anymore. You're just talking about instantaneous transfer of information. And that would also be really interesting. Where we are with quantum computing right now, it looks like, if you can believe the reports, that China is drifting into the lead. Google's efforts have also been very performant, as have IBM's. And so but none of them have reached a point where we think that quantum computing can displace classical computing, and there's an increasing group of people that believe it may never. That much like you wouldn't use a semi truck to commute to and from work. Well, I guess you could, but you wouldn't. There are things that classical computers will always just simply be better at. It's not that quantum computing couldn't do the tasks, but the cost of using a quantum computer would just simply be wasteful. Quantum computing does take a significant amount of power. Right now, you have to operate at sub-zero temperatures, significantly sub-zero temperatures, to make the stuff work. And the thought that quantum computing at any time in the future will replace classical computing is still often the distance and may never occur. So the two things right now are kind of bifurcating into different areas. Classical computing is actually moving into quantum computing space, and quantum computing has not reached the point where it is viable yet. We're getting closer every year, but quantum computing remains largely a theoretical concept with lots of proof and concepts that showcase that quantum computing can be done, but it just can't be done yet at scale. And so with generative AI, we're showcasing, and of course with AGI on the horizon, we're showcasing we can do more and more with existing technologies, and the need for quantum computing has dropped off rather significantly over the last couple of years. So that's kind of the start. They're very different approaches to analysis, and in both cases, we're talking about analysis for the most part. By the way, it's very likely that when we finally do get quantum computing working, we'll likely have it wedded with classical computing, and it'll simply, much like we do today when we have multiple instances in the cloud, and we can move between instances depending on our performance needs. It is very likely that's the way we're going to deploy quantum computing as well. You as the need increases and starts to bypass classical computing, you will fail over to a quantum computing instance, and then it will take over and handle that portion of the problem or problems that the classical computing can't handle. So that's my opening.
Thank you. Mr. David, my first question for you: how did classical physics based on Newtonian mechanics and Maxwell equations shape our early understanding of the physical world, and what were its limitations?
Oh, I'm sure glad you're getting this one.
Yeah, I am too. Rob did an excellent job of saying part of the foundation here, and I want to expand a couple of his points as I begin to answer your question there, Sharif. If you look at classical computing, classic physics, it really is characterized by predictivity in its intuitive nature. So in classical physics, you really calculate the exact position and where objects are going, where computations are going, given their initial conditions. And so it's great in many things. I mean, classical mechanics with thermodynamics, classical wave theory, the classical physics, the classical computation really is what's driven the industrial revolution and it's really to where we've gone today. Where quantum physics, on the other side, explains things that classical physics cannot explain. A good example is behavior of electrons and atoms or the nature of light. So the big difference is where classical physics is predictable, intuitive. Quantum is really not predictable there. It really looks at how to begin to understand the nature of it. So it's probabilistic, and it describes the behavior in terms of wave functions and probabilities, and not the exact positions and the exact things. So you see some of those big differences there as you look at some of the trends that are there. Now, to get to the details of your question, and Rob, I hope I do justice with this, with getting into some of the details, is Newtonian physics is really the bedrock of classical physics. And this really began back in the 17th century. And Newton came out with 3 laws. The first law is inertia. The second law is F equals ma. which is the force acting on an object is equal to the mass of the object multiplied by its acceleration. I'm sorry, the first law is basically an object at rest remains at rest, an object in motion continues in motion at a constant velocity until acted upon by other forces. But the third law is action reaction. For every reaction, there's an equal and opposite reaction. And so this is where the Newtonian base mechanics really come into place. And those three laws, and then Newton's some of the extensions, and then Einstein's extensions to Newtonian work are really what's driven us to where we are today in the whole classic side of this. So like Maxwell equation in there was a unification theory across classical here. And he unified the theories of electricity and magnetism. And he had four laws that really went into there. And most of them aren't important, but the amperage law is one, which is how magnetic fields change current. You have induction magnetism and just the basis laws for his. But his laws is what set the places in the conditions in place for us to generate the communication systems we use today, to generate electric generators and transformers, and really provide part of the fundamental basis of what we do with computer chips. Now, part of the limitations, though, of the Newtonian and Maxwell and others is that there's things it can't explain, which is where the quantum physics comes in and does good. So classical really has a hard explaining microscopic phenomenon. So it's classic physics really can't explain atoms, electrons, and subatomic particles pretty well at all. And that's where quantum comes in and does a good job there, because classical physics and classical mechanics really is deterministic. And this is what we talked about last time we went through some of this topic with you, Dr. Shri. It means it predicts the exact outcome given the initial conditions. And so the classical physics is very exact, where some of the things, as we look at the example I just gave with the microscopic stuff, they're not exact going there. And the probabilistic nature I talked about earlier, quantum mechanics, is what really challenges that deterministic nature. And classical physics, classical mechanics, really has failures at speeds close to the speed of light and strong gravitational fields. And that's why Einstein came up with, he made extensions to the classical physics. And that's where you saw Einstein's theory of relativity come in. And Einstein's theory of relativity, particularly his extension to the Einstein theory of relativity, where he gets into some of the spookiness of what you see in quantum. I mean, Einstein's comment when he was introduced to quantum physics and quantum mechanics is it's spooky science. And it really is there because of the fact it can be in multiple states at the same time. It can be in all the other different areas. And that makes it where classical is very precise. Quantum is not. And I agree with Rob on where quantum computing is going. The quantum computers we see in the marketplace today, like D-Wave and others, the new announcement from Microsoft, the new announcement from Meta, these are all classic quantum effect machines, where the quantum computer that Rob referenced, for example, in China, the quantum computer he referenced with IBM, are classical quantum, and trying to move that forward is still a ways to go. But quantum effect machines are actually being done now in low temperature means, but they're hybrid effects, and they're often being combined with other types of processors like nanomorphic processors and neural net. So you're seeing that going as a way, but it's a really fast moving field right now where classical physics has been centuries and centuries. What we're seeing with quantum right now is moving very fast. So I hope this answered that question without getting too deep.
Thank you. Thank you. Thank you. Mr. Rob, my next question for you. What key experiments, such as the double slit experiment and the photoelectric effort, lead to the rise of quantum mechanics, challenging classical physics? Or you want to say?
Yeah, good luck. So now I'm wishing that I got the last one and Dave got this one. I'm not familiar with either one of these, so I'm not going to try to BS my way through it. I'm not familiar. David, do you know the answer to this one?
I think I do.
Why don't you give it a shot?
Okay, Sharif, let me go ahead then.
Yeah.
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 Yeah, I've been blessed. One of my mentors here and a guy I work with received the Academy of Physics Lifetime Contribution Award a few years ago. And I've gotten to be able to sit down with Hal and talk a little bit about these and among them. So there's multiple experiments that really play a crucial role as you look at these changes. And the double slit is one of them. So double slit was performed early 1800s, and it demonstrated the wave-like nature of light. So basically what it did is Thomas Young, I think it was Thomas Young, made two very closely placed slits, and he projected light through it. And he looked at the pattern on a screen displaying inference patterns, inference fringes, which is the characteristics of a wave. And so if you look at light, at the different frequencies of light, it's not a straight line. It's curves, it's frequencies. And these frequencies is part of the basis of the quantum mechanics. And he was, for the first time, this double slit experiment was for the first time lets you see the characteristics of wave behavior. Because always before it was just a theory. And then after the line, this double slit experiment was repeated with electrons, other particles and things. And so what it revealed was the quantum phenomenon of how it is. And so the couple big things out of that was the concept of, we talked about this last time, Sri, quantum superpositioning, where particles could exist in multiple states simultaneously. And the only time they collapsed to a exact state or a definitive state is when it was measured. But that when these were not being measured, it could exist in multiple states simultaneously. And then there was a wave particle duality that was there. And what it was is kind of interesting that when he basically pushed electrons through one by one through the slits, they still produced an inference pattern. And that really demonstrated that in quantum, in particular, that each wave is an inference. Each electron by itself is a wave, behaved as a wave, and it interfaced with itself. And see, this really contradicted classical physics, where electrons were treated as particles. It's a discrete particle, where in quantum, it's really a wave with this multiple states, multiple frequencies and things that go into it. So the double slit experiments set a lot of the fundamentals in place that quantum was built up onto, and really there. And then the other one you asked for in this one,
Photoelectric effect.
is the photoelectric effect. And this also originated in the 1800s, but Einstein really took this one and ran with it a lot more. So it provided the evidence that for the particle nature of light. And in this one, what the simple outcome was, is trying to not get deep into it, is that when you shine light like on a metal surface, it causes the electrons from the metal to combine and work with it, and to immerse from it. I guess that's probably the best way to describe it. So some of the key findings of this one is that classical wave theory can explain why the ejection of these electrons, the movement of these electrons, depend on the frequency rather than the intensity of light. And a good way to look at that is when you look at, for example, different types of light bulbs. You have cool white light bulbs, you have daylight light bulbs, you have all these different colors. It's still light, but the frequency of all those is different, which is causing you to see some of those color differences. But what Einstein proposed on the photoelectric effect is that light consists of packets of energy called photons. And each of these photons, the energy in it is proportional to its frequency. A good example today is when we started using fiber optics cables to carry data. They started out with being single frequency, and it could only carry a little bit. Then they became dense waveform and multiple frequencies, multiple colors of light in essence. And that's part of what this set the stage for going forward. In there. And again, what this one did is, again, build upon the quantum duality, that it demonstrated that light exhibited both wave light and particle light properties. And this really challenged the basic classical physics that said, no, light was just a particle, not a wave. But there was a duality there. And then let me just kind of throw you a couple of other key ones out there. I'm not going to go through all of them. But the other ones that built up on this was one called the Crampton effect, which was X-rays being scattered, changed their wavelengths. And that reinforced the duality again. And then you had Planck's hypothesis, that he said that the energy of radiation can be quantized. And this quantums really marked that spectrum has a black body radiation. But Max Planck's theory here marked the birth of quantum theory, and this began about 1900. And then there's so many other ones. I mean, you get into there's half a dozen others of these that plays just in here. But what these experiments did is they challenged the classical physics framework, and they paved the way for the development of quantum mechanics, and particularly the dual wave, the nature, and how things could be understood in multiple states at one time. So, Rob, I hope I did justice.
Thank you. Thank you. Mr. Rob, you want to respond to this question? How do the principle of determinism in classical physics contract with the probabilistic nature of quantum mechanism?
So the deterministic nature of classical physics really looks at large objects, relatively large objects. down to molecular level, but the molecular and larger. Quantum physics tends to focus at some atomic levels, and so the deterministic nature of regular physics means you have a solid answer to a problem. Yes or no, will it occur? The probabilistic nature of quantum physics says you have a probability of a certain outcome, and it's a different. Nothing is absolute. It's always probable. In a deterministic system, x plus y always equals z. In a probabilistic system, x plus y has a 99.999 chance of being z. There's always a probability of that occurrence, not the occurrence that you're predicting, not occurring. Could be very small, but it's still something that quantum physics addresses. When you're talking about, again, the example I gave before about the butterfly flapping its wings in China affecting the weather in the U.S., quantum computing can embrace that problem. The classical physics, quantum physics embrace that problem. Classical physics, not easily. The amount of computing power that you would need for classical computing to make that determination you're probably talking about hundreds, if not thousands, if not millions of years. Where quantum computing, assuming it had the adequate data, would be able to make the determination relatively quickly. Some of the interesting aspects, of course, of quantum computing versus physical computing is when it comes to cryptography. With classical computing, the cryptography, you can create keys that are virtually unbreakable. With quantum computing, you can't. The quantum computing will be able to determine and break pretty much any classical computing key in a matter of moments. So your level of being able to defend against a quantum computing attack is substantially reduced. We do have, interesting note, we do have quantum defense programs in place by HP, IBM, and I'm sure some others. Until we have quantum computing, we don't know if they're going to work. But what they're doing is they're breaking down the problem in a way that makes it very difficult for a quantum computer to address it. And so where if you were talking about classical computing, as I said, you can create defenses that work just fine. So it's the nature of how both systems look at a problem. In a deterministic model, they look at a problem in terms of absolutes. In a probabilistic model, they don't. There are no absolutes. There's always a remote chance that something else will happen, and it wants to know how big that remote chance is. To give an example of a real world problem, when they're building the Hadron Collider, they used classical calculation techniques, and they made a determination of how unlikely it was that the Hadron Collider would create a black hole and destroy the planet and possibly the solar system, if not a larger component of the galaxy. And it seemed very remote. As they advanced their theoretical analysis, they discovered they were several magnitudes off in the wrong direction. With quantum computing, you would get a much more accurate, I should say, probability of whether something like that would occur, and thus you could make a better decision about whether you want to take that particular risk. Personally, I'm the view when you're messing with something that could destroy the planet you're living on catastrophically and relatively instantaneously, that perhaps you should err on the side of caution as opposed to saying, yeah, let's go try it out. And so with quantum computing, you get a better sense of the risks you're taking. They may be minuscule, and they may not be, because it's looking at things that deterministic physics are not looking at. And so the end result is you get a better idea of what's actually going to occur. You get a better sense of the world around you and how it interacts, because you're operating at a subatomic level. As David pointed out, when you get down to subatomic levels, things that you think of as things may actually behave as waves. And so your fundamental underlying theory is at risk, a risk of being absolutely wrong. And so quantum deals with that nature of a problem so that you get a better understanding of the risks you're taking on a particular decision. It's not that one necessarily replaces the other, but quantum physics can add a nuance to what classical physics does that allows you to make a better determination of the risk that you're taking or the probability that the outcome that you are predicting may be wrong. And that way, if you're dealing with something like the destruction of the planet, you can make a much more informed decision if that's a risk that you want to take. I'm still of the view of, even if it's out 5 or 6 decimal places, I don't think that risk is going to be worth it, because it's pretty hard to move off the planet right now and move to something else. But that's what quantum physics would get you to. It would show you just how much money or how much effort you should be making in terms of mitigating a particular problem, where a deterministic approach might convince you there was no problem to be worried about. It's the nature of how these things approach a particular issue. Deterministic looks at the big picture and makes an absolute statement that could be absolutely wrong. Quantum physics looks at it and makes a probabilistic statement that says, here's the chance you could be wrong. And when you're looking at major events, you do want to kind of consider this chance, and particularly when you're looking at things on a universal nature, where you've got a lot of elements that are in motion. That probability of failure could come up quite rapidly, where deterministic physics wouldn't see it. The quantum analysis would showcase that maybe this is something you might want to consider, because it is much more likely than you thought it was with a classical approach. Hope that does it.
Thank you.
Remember,
before you ask this
we
one,
probably have a physicist on this call, but yes.
Rob's example is a great one, because like today there's an asteroid flying by the Earth. But the big asteroid that was in the press 3 weeks ago or so was one that could potentially be very life-threatening. And they did both. They did precise measurements of it in the few windows they could see it, using a classical approach, but then they used some quantum-like approaches to really look at what are the other potential impacts. So oftentimes what you really want to do is you want to use both a classical and a quantum approach when you particularly deal with big problems. And that's the places where I think what you're trying to show, Sharif, comes to light here. Just like we talk about different AI tools, you don't want to use just one. You want to use multiple. Same thing when you look at classical and quantum mechanics. You want to use both of them as you look at these type of issues. But sorry, Sharif, Rob's example was so good with what's happening now to show that example.
Thank you. My next question, what are the major philosophical and technological impact of quantum mechanics that distinguish it from classical physics in the field like computing, cryptography, and artificial intelligence?
Well, I think I kind of mentioned that before. The major philosophical and technological impacts really come down to not looking at things as absolutes. Really saying that there are other things in play that we may not be able to see. We may not be able to even measure yet. That are going to have an impact on a particular answer that we're trying to come up with. When we talk about computing, this really only comes into play when we're talking about incredibly large data sets, a lot of moving objects. The more complex the problem, the more quantum computing shines. The less complex the problem, the more classical computing shines. And when you get into cryptography, as I mentioned before, today we can create cryptography that is resilient to virtually any classical computing attack for a near infinite amount of time. I say near infinite, given enough power and enough capability, you can probably still break anything, but it just might take 1,000 years or something, 1,000,000 years or whatever. The issue, of course, we have with cryptography is data that's been stolen and is at rest. So somebody has stolen a data set that is protected by cryptography, but they have the data set. They can't analyze it. They can't look at the data. But now quantum computing becomes real. The quantum computer can look at the data, analyze it at a very minuscule level, and make a determination of what that data likely means, what the information in that data actually is. And it can do so very quickly, regardless of the amount of complexity we build into the system. So it really changes the game with regard to cryptography, where virtually everything that we currently have, with the possible exception of things that have been made quantum safe, which still has to be tested because we don't really have quantum computers that can test it yet. But it would virtually change how we do things. One interesting thing about the quantum computing is you can measure when something's been observed. When something's been observed, you will know it. So with the typical data stream, somebody was able to tap into the data stream as long as they didn't compromise the data. You wouldn't know it was compromised. With quantum computing, as soon as somebody observes the data, it changes the outcome. I hate to use Shorter's cat for this because that was more of a joke than a statement. But the idea of you have a cat in either alive or dead, and it's not until you open the box that you can determine and see the cat that you can make that determination. That it's that very act of opening and observing that changes the data stream in a way that quantum computing can detect. And so now it doesn't matter whether or not somebody can understand what it is you've been transmitting. You will know immediately if the data stream has been compromised. Now, with artificial intelligence, we get into something that gets a little bit more interesting. And why I say more interesting is I don't think quantum computing has a play with standard artificial intelligence. Artificial superintelligence is where quantum computing comes in play, because when we talk about artificial intelligence, even AGI, we're talking about being able to do things like people do them, maybe faster. But the approach to the underlying problems are very much like we might approach an underlying problem. You include quantum computing, you basically get kind of a godlike effect to the solution, the ability to see and observe things that we ourselves cannot see and observe, and even if we were able to, with the proper equipment, to see and observe it, we wouldn't be able to make determinations quickly enough if we're talking about a real-time event and come up with a solution in time to avoid the overall outcome. In most cases, David used the meteor as an example. If we were really to try to understand all the different elements that come into play with that meteor that could impact the Earth, I would almost guarantee you that would change the probability of the impact. Either way, that wouldn't necessarily be more chance of hitting the Earth or less. It could be either. But the quantum computing approach would come up with a far more accurate answer. And the screwy thing is it still wouldn't be absolute. It would still be probabilistic in nature. So there would still be a chance that answer would be a different answer. In fact, when you look at quantum computing, it doesn't deal in absolutes. It deals in probabilities. And so the overall approach to the answer, the overall construction of the answer becomes far different. But if you were concerned about that thing hitting your house and you wanted to know whether or not you should spend the next week in New York, the quantum approach would give you a much better understanding of what your risk is, while the deterministic approach of classical computing would imply that you're absolutely safe, and you shouldn't hide out or dig a hole in your basement and pull the hole in after you. So it really kind of depends on the application of the technology. But with regard to AI, we're talking about the capability of creating an artificial intelligence that has massively more capability than we understand. If we were to think about it and define what "quote unquote" a godlike entity would be, AI superintelligence with a quantum computing foundation would be that. It would have an understanding well beyond our own capability, without something like the singularity or a blending of human and machine capabilities. We just don't have the capability of being able to fully solve a quantum computing ourselves. We can do what AIs can do. Classical computing AIs, it might take us longer, but it is within human capability to do. You put quantum computing on top of classical computing, and suddenly you have a capability that biologically we probably couldn't get to in a couple billion years. It's a completely different way of solving problems than we're capable of handling. And so that kind of computer, that kind of AI, would have a capability that at least right now, I'm not even sure we could fully describe, but it would be vastly more capable than an AGI that we're currently talking about.
Thank you. Mr. David, what are the major philosophical and technological impact of quantum mechanics that distinguish it from classical physics in fields like computing, cryptography, and artificial intelligence?
Rob's done a pretty good job of touching many of those elements, and uh, you really have to look at the differences there. And the biggest difference is how they look at the different ways to understand the deterministic versus probabilistic. And you really have to understand that. One of the big differences is you look at the ones that you're talking about is something called non-locality. And uh, Rob mentioned at the top of your show the whole area of quantum entanglements. And these quantum entanglements introduces this concept where non-locality, where the state of one particle is instantaneously correlated with the state of another one. And this is where it gets really interesting because that non-locality, it doesn't matter how much distance is between those 2 points. And that's where quantum teleportation, where quantum superpositioning and everything come into play, is the state here. So as you're looking at this, Dr. Shreve, that is one of the major philosophical or technology impacts as you get there is understanding this state where in classical physics, I can almost reach out and touch, not literally, but you understand the things in a much more detailed manner. And, you know, the philosophical side you ask in this question is an interesting one because quantum and the probabilistic nature of quantum mechanics really raises philosophical questions about the nature of reality. And is it a common reality or is it multiple realities at the same time? So this is where you look at Einstein's extensions to the theory of probability. This is where the idea of multi-dimensions come from. And are we just in one of multiple dimensions that are happening simultaneously even? And that's one of the big philosophical things there. Also, the philosophical nature is what is the role of the observer? What is the limits of human knowledge is a philosophical question. And that the interpretations of quantum mechanics are broad and many. There's something called the Copenhagen interpretation. There's many worlds. The different types of wave theories are some of them. But you know, the principles of determinism in classical physics really contrast very sharply with the probabilistic nature of quantum mechanics. And the two of these mesh together really has revolutionized our understanding of the physical world, and particularly new concepts. And it challenges me, the classical things that have been centuries and centuries and centuries as physics is coming to place. And what is interesting is we still have not gotten to any truisms on this. We're still trying to figure out what this intersection of the quantum world and the classical world is. I mean, there's one of the comments I saw just rolling through the comments earlier was it seems that the two of these bring together the virtual and physical realms into the same harmony, which is not a bad comment when you start looking at this at the philosophical level and the technology impacts that you asked in the question, Dr. Shree.
Thank you. My next question for Mr. Rob: how does the quest for a unified theory, such as quantum gravity or string theory, seeks to bridge the gap between classical and quantum physics? What challenges remain? Or
This is kind of the answer you need Sheldon Cooper for out of Big Bang Theory. He spent the most of the show trying to figure out string theory and then finally gave up, I think, in season 4. So when you say bridge, I still see the two underlying practices as being somewhat separate. That they're basically different approaches to how you solve a problem. With quantum physics being where the heavy lifting is and where much of the theoretical work is. And when I say theoretical, I mean quantum physics still has a huge basis in theory. I mean, that's the one thing I took away from the Big Bang Theory it's highly theoretical, and the ability to prove the underlying concepts has been somewhat elusive. Yes, we are building quantum computers, but we don't yet have one that's performant, and we don't even have really, and we haven't for some time had a timeline for when we will get to quantum supremacy. And there are even people now that are arguing that maybe we never will, and maybe we don't want to. The idea of quantum computing being able to take over the role of classical computing is a false goal. That quantum physics is just a very different way of looking at different things, and it isn't necessarily appropriate to use it every place. I mean, do you really need to use quantum computing for architecture, for instance? Probably not. You need to use it for finance? Probably not. But you do kind of need to do it if you're calculating whether or not an asteroid is going to hit the planet and wipe out all life on Earth. That's probably where you want to use quantum physics. When you talk about bridge, because the underlying fundamentals are different, the way both elements approach a problem are different, and neither one is wrong. Each one has, or I shouldn't say that. Both of them could be wrong. The question is at least the concept I have in my head is, at least with quantum physics, it tries to calculate to a much higher degree the probability of being wrong than classical physics does. It at its core, quantum computing recognizes that nothing is absolute, where classical physics does kind of imply that most things are absolute, and that's important for certain things. I mean, do you really need to know that when you get out of the bed in the morning, there's a 0.999, not 0.0000001 chance that you're going to go up instead of down when you step out of your bed? And probably didn't put enough zeros there, like a million zeros that you might. No, you're gonna step and you're gonna land on the floor. On the other hand, if you're blasting off a spaceship and you want to land safely on Mars, maybe that's a number that you want to consider. At least you want to understand all the underlying elements, because otherwise you might not end up in the place that you want to end up. You're flashing a lot of questions here on the screen at once. Did you want me to address those others? But at least from my perspective, this idea of bridging the two doesn't make a ton of sense to me. I'm not sure you have to bridge the two. They are simply different approaches that have a higher, that have a better chance of addressing certain classes of problems. Much like you have different tools in the tool chest when you're working on an automobile, somebody that's trying to solve problems has different tools that they can use to solve problems depending on the nature of the problem. And quantum computing's approach presupposes a different problem that classical computing probably can't address appropriately. And so you have this hierarchy of problems. The vast majority of problems we believe at this particular point in time can be addressed by classical physics. However, we don't have a universal knowledge of all the problems that are out there, all the potential calculations that are out there. And my sense is that with classical physics, you have a ceiling. With quantum physics, you do not. But that's only because we don't know what comes after quantum physics. I would say if there's a hierarchy of this classical physics, quantum physics would reside on top of that, because it looks at things far more deeply. And there's a chance there's something, because we didn't really know what quantum physics a couple hundred years ago, that there's something that may overlay quantum physics that we haven't yet explored, and we may not even understand until we fully understand quantum physics. So the result is each discipline is very different. With quantum computing, you do need to have a firm basis in physics. For classical computing, you do not. That you can be an expert in classical computing without any because I'm an expert in classical computing and I don't have a strong physics foundation. With quantum physics, you have to have a strong basis in physics, particularly in quantum physics. So they're fundamentally different. And I don't know if you can bridge that. I don't know if you can or would even want to bridge that difference. Much like you say, okay, I got a screwdriver, I have a wrench. Let's create a screwdriver wrench. It's probably going to suck as a screwdriver and it's going to suck as a wrench. It's like amphibious cars or automobile. I'll tell you stories. Sometime I'll tell you the story about the Pinot flying car, but the didn't end well. So they're different categories of analysis, and they lend themselves to different categories of problems. When you try to have the two disciplines work together, and you may, as I mentioned before, with computing, you very well may have a hierarchy where you put forth a problem, and the classical computer takes breaks the problem apart. It takes the part of the problem that it can deal with, and then the quantum computer takes the part of the problem that it can deal with, and then you have a bridge that gives you a conclusion that you can work with. That bridge at some point will be very important. I don't think we're there yet. But that's a different kind of bridge. That's not a bridge between theories. That's a bridge between operations. And so that kind of a bridge I expect we're going to need, the operational bridge. The bridge between theoretical approaches, I'm not sure we necessarily need that kind of a bridge. I think we need to focus and understand the differences, but I'm not sure we need to bridge them. At least in my head, I haven't come up with a reason for a theoretical bridge between the disciplines. The operational, yes, but not theoretically.
Thank you.
Again, not a quantum physicist.
Yeah, Mr. David, you want to respond to these questions?
Sure. I want to build up on what Rob's talking about, though. And I'm going to go back to just not the quantum physics or the classical physics, but I'm going to use it from computation. The very first computer was an analog computer. And there's actually still places today where analog computers are good because of the nature of the fuzziness of analog measurements. And then we came along and we went to the place where we have classical computers, CMOS computers, and they became much more precise because of what we were having to deal with. Then our data sets got bigger, the problems got harder. We were trying to do global forecasts. We were trying to do all these other things, and that's where really the concept of quantum computers excels, is looking at very big, hard problems and very small, tough problems. I was fortunate to actually led the first quantum computing roadmap in the United States way back in the early 90s. But then what I did a few years later is I led the first biological computing. And biological computing is real interesting because what biological computing does is it takes the concept of our neural networks and expands it to where we're taking those other three concepts and merging them in multiple parallelism. But then we have new types of computation coming out. One of the next big computers you're going to see is a photon computer using the particles of light as a computing engine. And that's going to, again, extend what we've learned in classical physics, what we've learned in quantum physics, and trying to extend them in ways that we can reach this hybrid nature of what we're trying to do with this. And, there's constraints in each of them. There's places where they really fail. And there's places each of them exceed very well. But we've got to take and pull these together, because you need to have, as we look at these harder problems, as we look at really the nature of what's there. Because I remember when I was back in college and looking at some of the physics classes I took, look at some of the engineering classes I took, and some of the things we learned then as fact were not fact at all. As we begin to learn more and continue to go. So what we see is that there's this evolution of physics. I have a feeling that in the next 6 months or so, there's going to be some things that are announced, that are disclosed, that are going to fundamentally shape part of our understanding of classical physics and quantum physics quite a bit more as those things are disclosed. And so we're going to have to continually, I hate to use my term again, we're in lifetime learning. And in classical physics and quantum physics, we're still there, we're still learning. And this concept really is there because we are limited as humans what we can observe and what we can know. And as we continue to observe more and know more, we're continuing to expand these. That's one of the things I love when Einstein did his extensions to the theory of relativity. He says, there's stuff I don't know, but here's what I think is coming. And that's what his extensions are. And we're going to be doing the same things because we are going to push our knowledge so hard and our framework so hard that we're going to have to do something to continue to learn, to continue to go through these. And, you know, you see those. Quantum gravity is one that is just getting so interesting because there's something where Rob mentioned the string theory approach that Sheldon talks to all the time. But quantum gravity and quantum loop gravity is a non-string theory approach to quantum gravity that quantizes space-time itself and the space-time metrics that you've heard about in science fiction and things actually becomes supported with that. And the string theory, which Rob referenced up there, is really, it really says that the fundamental building blocks of the universe are not point-like particles, but they are one-dimensional strings that vibrate at different frequencies. And that this string theory has something called the theory of everything. And it is there because it has this supersymmetrics in it that is trying to force all these theories together in the classical and the quantum. And it came up with something, see if I can get the name right. It's the M theory. And it's an extension of these that unifies the different versions of all the things that Rob and I have been talking about today. And it proposes that there's an 11-dimensional framework that includes something called banes. And these banes, it says, are the next area that our approaches to physics is going to go to. And in classical physics, classical quantum physics do not exist in 11 dimensions. And M theory says it should exist in 11 dimensions. And that's hurting my mind just thinking about it right now. But that is where these type of things still have a lot of work to do, a lot of science. And Rob, you talked about not being the physicist on this for the quantum side. It's not just physics, it's material science, it's mechanical science, it's philosophy, it's biology. All of these are necessary today to understand where quantum is, and not just the classical physics and material science that was required for classic physics. So Sharif, my head's hurting for my answer, but that's really where this is going.
Thank you. Mr.
Nice
Rob, what's your closing remarks for today?
Oh, for me?
Yeah.
Yeah. So I'm mostly on the quantum side. So on my side, the quantum computing side, the not quantum physics. So that when it comes to quantum computing, recognize that what really makes it different is its probabilistic nature and the amount of data that it can consume and pull information out of. Its approach is fundamentally different. And if we can solve this particular problem and bring quantum computing to market, it will be a game changer for some of the more difficult problems we struggle with. Some of the bigger issues that it's very possible by understanding quantum computing, we could better understand we can understand at a much deeper level the nature of our bodies and our existence as it relates to other intelligent or non-intelligent things. The level of analysis that quantum computing can bring to any difficult to solve problem is right now immeasurable. And I'm not saying immeasurable as it doesn't exist. I mean immeasurable in terms of the benefit could be far greater than even I think. The underlying interesting issue is how quickly AI is coming up to use a predictive element to reach the same kind and potentially the same quality of problem, assuming we can get the error problem with AI worked out, which seems to be working a little better in China with DeepSeek than it is in the U.S. with ChatGPT at the moment, but that with the obvious exception of Chinese government interference. So in the end, quantum computing will make a massive difference in how we look at the world, make a massive difference in being able to solve problems we are currently struggling with, and make a massive difference on what we can do or even want to do in the future. The question we have to ask ourselves is will we accept the answers that we will get? And that's always been a problem with any level of science.
Thank you, Mr. David. What's your closing remarks for today?
Well, thank you again for a topic today that's totally stretched me and is forcing me to go back into things that I tried to forget because they were so complex and complicated. But yeah, I think the big thing today is what are some of the challenges? What are some of the open questions that we need to deal with? One of the biggest challenges we have, and this is something I learned in the semiconductor industry, of all places, is we need to do experimental verification of this. And in the classic science and engineering, it's called design of experiments. But the biggest challenge is the lack of experimental evidence for all the theories in both of these. There's stuff that we see the effects of, but we don't know what causes the effects. And that's why Einstein called it spooky, is because you can see something, but you don't know why it's happening. And so we really have to have this experimental verification. And the energy scales that are required to test things like quantum gravity and string theory and some of the quantum teleportation and some of the superpositioning are beyond the reach of the existing technology we have. So we have to invent new technology to understand what we're talking about. And so that's one of the big challenges there. And the mathematical complexity of this is a real ongoing challenge because it's taking us beyond where our theory can deal with the mathematical complexity. And there's a couple of other things. There's something called background independence, where particularly in quantum, and when we get into like M theory and string theory and these others that were brought up, they're not background independent because they rely on I hate to put it this way, a fixed space-time bit in there. And we realize that our understanding of the space-time dimensions are changing and dramatically changing. Now, Rob mentioned the black hole earlier with the hyper collider. Even understanding something like a black hole, which these should explain, and that's part of this, we can't explain. So that is there. And there's just two last things, is that there's something called unification of forces. And it's trying to push all of these together. And this unification of forces, we can't do yet. And it really is the thing there. So there is a quest for unified theory, but we don't have it. And we're looking for the bridge that was referred to earlier between classical and quantum physics. And we still don't have one. And my personal feeling is where I see the science going, that gap for that bridge is going to get wider and it's going to get closed over the next 5 years or so. So is it going to be an evolution? It's going to be an ongoing evolution of physics that's going to be exciting for all of us. And who knows, maybe I need to go back and take new physics classes again. But Sharif, thank you so much.
Thank you. Thank you. This is excellent discussions. I think there are a lot of audience has their own response about quantum computing. This is very interesting. I request all of our audience, please share our content as much as possible with the government agency, corporations, and academia. Thank you, Mr. David Smith, and thank you, Mr. Rob, for your continuous support for World Talent Economic Forum. Thank you. Bye-bye, and take care.